I recently published a video showing a series of experiments with the application of the concept of pursuit curves to geometry. You can get pretty interesting results, and I thought it could be an interesting subject to share through a tutorial. If you go to Wikipedia, if you look for a definition on curve pursuit, it will state that a curve pursuit is a curve constructed by analogy to having a point or points representing pursuers and pursuees. The curve pursuit is the curve traced by the pursuers. Another definition I found says that a pursuit curve is actually the path taken by a point that is always moving towards another moving point. Going into Houdini, here you can see we have 4 points, and running that concept, that algorithm, each point will have its own ID, and right now what we'll be seeing is that each point will be pursuing its neighbor clockwise. When we do that, what happens is that they will display these beautiful curves. And when you connect each pursuer to its pursuee, you'll get something like this, and these very interesting patterns. Now let's see how we can create this simple algorithm in Houdini. Okay, back to Houdini. First thing we need to do is create a geonode as usual. We need points. We'll start with 4 points, so I'll create a grid 2 by 2. I'll switch to top view, spacebar 2, disable my grid. So we have 4 points to start. Now our points will need IDs next, and for our IDs I'm going to be using the point number. But right now we do have an issue, which is the fact that the point number isn't going in the order that we would like. We will need them to be in clockwise or counterclockwise order, because right now if we use the point numbers for the IDs and for defining the targets for each point, what will happen is that 0 will follow 1, 1 will follow 2, and 2 will follow 3. So we'll get something of a crossing here. So ideally we would have 0, 1, 2, 3, 0. Okay. The way to solve that is with a sort node, and we could use the vertex order that actually defines the primitive polygon face. So if we use that, if we switch the point sorting by vertex order, you'll see that we get 0, 1, 2, 3, and that's exactly what we wanted. So now we can delete the face. We don't need the geometry anymore. Now we just have the points. So let's start assigning IDs. So I'll create a point triangle. I'll keep things separate. You might want to do everything in the same place, but usually keeping it separate is not a bad idea if you're organizing your approach to something new. So I'll call this assign IDs, and like I said, I'll create an integer attribute called ID, and it's going to be equal to my point number, ptnum. Having some troubles here with the keyboard. Point number. Let's check our geometry spreadsheet, and it's matching, it's there, so we're good to go. Continue. Let's create a new point triangle, and this point triangle I'm going to call it assign targets. And here again we'll use the point number as a starting point, so we can say that I'll create a integer attribute called target ID, and this target ID is going to be equal to the point number plus 1. Okay, so what we want is we want for 0 to chase 1, 1 to chase 2, 2 to chase 3, and 3 to chase 0. With just this expression, what will happen is 3 will chase 4, which doesn't exist. So we need to account for that situation. If my target ID is equal to the number of points in my input, which is what will happen, okay, I have 4 points. My IDs should be only going from 0 to 3. So we can use this expression to account for the situation where we have a target ID that goes above the ones that are available. We can say endpoints on 0. Okay, so if my target ID is equal to the number of points coming in on input 0, then in that case, I want my target ID to be equal to 0. Okay, that solves it. Next, let's start working on the actual algorithm on itself. So let's create a new point triangle. I'll say, call this calculate new pause. And here we first need to find our target. So let's go to integer, and the reason for that is that eventually we will have a lot of points. Right now we could use just point number. It seems pretty simplified, but we need to actually find the point that has the ID that matches our point's target ID. So we need to create something a bit more robust. So my target is equal to find attrib val. This command allows us to find the point that has a certain value for a certain attribute, and in our case we want to find the point from geometry input 0. We want to find a point, it's a point attribute called ID, and it needs to match our target ID. Just click the I here. Okay, so now I know which point is my target. Let's find out what's my target's position. Vector target pause is equal to point from geometry 0. I want its position, and I want the position of my target. Now I have my target, I have my target position. Let's find out what's the direction that takes my point to its target position. So it's another vector, and in this case I'm going to call target there, the direction towards my target, and it's going to be a vector which I want to normalize. Okay, so it's just a direction, so I want to have it from 0 to 1. I'll normalize it. So normalizing basically just guarantees that the length of the vector that you're getting is going to be of 1. Normalize it, and I want to normalize is the vector that goes from me to my target, from my point to my target's point. So let's say target pause minus my current position. I have these 3 elements. What else? Let's see what should be the how do we calculate our next position. So I'll call my next position also, it's going to be a vector, and I'm going to call it next pause, and our next position is going to be equal to our current position plus a certain amount of movement in the direction of my target. Okay, so that means it's my target here times a certain step, a certain size, a certain distance. I'm going to call it step. This step doesn't is a variable that still doesn't exist. I'm going to create it right on top. It's a float. Let's call it step, and let's say it's equal to a channel, just so it's easier for us to adjust the parameter with a slider. And I'll call this channel step size. Let's create the channel. By default it's 0. If you don't remember to change this from 0 to something else, you might think that it's not working, but it's actually just because you forgot to change the default value of 0 to something else. Let's go to 0.5. And now all we need to do to see if this is actually working is try to update our position. So update our position means just saying that my position is going to be equal to my next position. And there you have it. I don't know if you saw that, but there was a little jump each point, moving from its initial position and one step towards the target. Okay, to see this in action and to see this continuously update, we'll place this inside of a solver. Just gonna copy this inside the solver. Let's first create a switch, and let's say I want to consider this input every time my current frame is above 1. Okay, so if I just write Shift F or $F below -2, this is what will happen because I'm at frame 1. So now my switch is considering its input 1, which is this one, which actually matches input 1 from the solver, which is actually 0, but it's kind of a confusion that you might get there. But having done this, I'm gonna paste, and I'll paste this here, activate this one, and we should see our points moving towards their targets. Let's remove this. To make this more visible, let's for now just create a trail node so you can actually see it better, what's happening. Okay, and we'll have a trail, and you can see the trajectory and the points giving origin, generating these really nice curves. Okay, you can of course go to the point triangle we created and reduce the step size, 0.2 for instance. Coming out again, reset simulation, and you should see a much finer, a slower progression and a finer curve. Okay, we're in track. Now what else? We need to let's start by connecting each pursuer to its pursuee. Okay, each point to its target. I'll start by doing this here. So I'll create a new prim. I'll call it's an integer. It returns an integer. Call new prim, and it's equal to add prim to geometry 0. It's a polyline type of primitive, and we need to give it 2 points. So I want to connect my current point number, current point ptnum, and I want to connect it with its target. Done. Okay. Now if we update this here in the solver as well, you'll see that we get this shape progressing, okay, and moving. If we activate our trail, you should see the final result. So this is pretty close to what I showed you before, but the difference is that we don't want to be depending on a trail. I think it's a good solution for some situations because it'll then disappear. This might be an effect that you're looking for, but I think it's a good idea to go over how you can actually generate your own trails and use that instead. So to generate our own trails, we first need to make a distinction between what are active points and what are trail points. So if you think about it, we only want to calculate the new position for the active points. The points that are being left behind, the trailing points, do not need to be processed by all these things that we're calculating here. Let's see how we can do that. One of the easiest ways would be for when we're assigning IDs, we can also assign a point group. Let's say integer group underscore, let's call it pursuit. So this is me stating that in the beginning, all points belong to the group pursuit. Okay. Now if we have a look at the at our spreadsheet, you'll see that all points belong to the group pursuit. And this calculate new pos will only have effect on the group pursuit. Now, what we'll do is, instead of moving our current points, we are not going to update the position here. And we're not going to keep, and we're going to keep this next position in a variable, in an attribute on our points. Okay, so vector, instead of a vector, instead of a local variable, let's save it as an attribute, a vector attribute, and let's not update this position. For now, I'm also going to disable the primitive, the line that generates the polyline. Okay, so we don't have any connection. We do have an X position stored. We do have a group pursuit defined. So after we've done this calculation on all the points that belong to the group pursuit, we'll create a new point wrangle. And this new point wrangle will allow us to create a new point at the new position. Create new points. This will also work only on the pursuit group. And so for each point, we're running this point wrangle over, this code over. We want to add another point. So it will return an integer, new pt equals to add point 0, and we'll use the position we stored before, next pos. Done. Okay, we created a new point. Now let's just take care of a few extra things. We don't just want to create the point at the next position. We also need to make sure that the new point that we create belongs to the pursuit group and inherits the previous point ID as well as the previous point's target. Okay, so let's start with the target. Set point attribute 0. The attribute that we want to set is the ID. The point that we want to affect is the new PT. And the value that we want to assign to it is actually our current points attribute ID. Okay, so as you can see, our new points, which are 4, 5, 6, 7, have inherited the previous points ID. Before this, our new point, if we disable this line, you'll see that our points don't have IDs. And points that don't have IDs will have -1. Okay, next, let's copy this and use exactly the same expression, or very, very similar, to establish our target ID. It's going to be equal to target ID. Okay, same thing. We now have ID, and we now have also inherited our target ID. Next, let's just set point group. Let's say that our point 0, the point group is pursuit, and the point is new PT, and let's say 1. Okay, as you saw, this changed from 0 to 1. Without this line of code, we have the new points do not belong to the group pursuit, and with this little line of code, our new points are now included in the group pursuit. Next, we've taken care of the new points, but we also need to update the old points, which are actually our current points on this point wrangle. So we need to make sure that these points will no longer belong to our group pursuit. So let's say I at group pursuit equals 0. So they no longer belong to the group pursuit. They will no longer be processed in the next step. And let's also get rid of the ID. -1. -1. Okay, we changed. The old points now do not have IDs. They're not important. just a way of making sure everything is separate. So we're done. We'll just turn back on this line that actually connects the points to their targets. Let's copy this, bring it to the solver. I'll delete this one, paste the new ones, switch, and we should see what we were looking for. Okay, cool. So this concludes the development of our curve pursuit algorithm. You can test it with a different number of points. So let's create a circle. Let's increase the radius, something similar to what we had. Let's say it's a polygon, and let's say we can have as many points as we want. I'll start with 3, just show you that it works fine as well. Solver, reset simulation, and you get the same effect with 3 points. You can have irregular faces. You can have scattered points that are not coplanar. You can play with it and create a lot of different types of effects with just this simple algorithm. So give it a try, build on it. Hope you find it interesting, and see you next time.